Following up on our previous tutorial in which we derived the total probability formula, we now work through an example, and that's the one that we have here. We're told that the probability that it rains any day in February is 0.2, and we're then told when it rains there is a 40% chance that students play football during their afternoon break. On the other hand, when it doesn't rain, there is a 90% chance that they play. We're then asked, what is the probability that students play football on February 15th? Now, before doing anything, it's important to realize or to recognize that we're dealing with conditional probability in this question. In other words, we need to ask ourselves, how can we tell that we're not dealing with independent events? And to answer that, we can start by defining the events that we actually have inside this question. And reading through this exercise again, it doesn't take us too long to see that there are two events, so I'll just write events. And those are, one, that it rains, so I'll just call that the event R. And two, that the students play football, so I'll just write football, and I'll call that event capital F. Now on top of that, as we read through this question, we quickly see that the probability that students play football is affected by whether or not it rains. Indeed, we can see that when it rains, there's a 40% chance that the students play football. And on the other hand, we're also told that when it doesn't rain, there is a 90% chance that the students play football. And that very clearly tells us that the likelihood of the students playing football is affected by whether or not it rains. The events R and F are therefore definitely not independent, and we're therefore dealing with conditional probability. And we can go further. Indeed, we can define which of the events is the hypothesis and which one is the event. And if you can't see which of R or F is the hypothesis and which is the event straight away, it's often a good idea to actually summarize all the probabilities that are given in mathematical notation, and usually you'll quickly be able to tell which one is which. So let's go ahead and do that. I'll do that on the right-hand side here. I'll say probabilities. Now, reading through the first sentence, the probability that it rains any day in February is 0.2. Well, in that case, it's quite clear. The probability that it rains is equal to 0.2. In the next sentence, when it rains, there is a 40% chance that students play football during their afternoon break. Well, we can translate this sentence in mathematical notation to say that the probability that they play football, given that it has rained, is 0.4, or 40%. So if I write that, that's the probability that the students play football, given that it has rained, is equal to 0.4. And looking at the next sentence, we're told, on the other hand, when it doesn't rain, there is a 90% chance that they play. In other words, a 90% chance that they play football. And again, we can translate this sentence into mathematical notation. So I'll just write that. The probability that the students play football, given that it hasn't rained, is equal to 0.9. Finally, looking at the last sentence, we are asked, what is the probability that students play football on February the 15th? Now let's be clear. Given that we were told at the beginning that the probability that it rains any day in February is 0.2, the fact that we're asked about a particular date, namely February 15th, has no effect on the overall problem. Meaning, we could have simply asked, what is the probability that students play football on any given day in February? So don't let this kind of information in a question confuse you. And this last sentence, or this question, gives us our target. Indeed, we need to find the probability that the students play football on any day in February, since that would be the same as the probability they play football on February 15th. All right, now that we've translated this entire exercise into mathematical notation, it's quite clear which of R and F is the hypothesis and which is the event. Indeed, we can now clearly see that F is the event and R is the hypothesis. And we want to find the probability that the students play football. In other words, the probability that the event occurs. And that's without knowing whether or not it has rained. In other words, without knowing whether or not the hypothesis is true or false. And this scenario, or this setup, is exactly what tells us to use the total probability formula. Remember, the total probability formula for an event A stated that the probability of event A occurring equals to the probability of event A and B occurring plus the probability of event A and not B occurring. And using the multiplicative property formula, which we also saw in one of our previous tutorials, we can rewrite this total probability formula as the probability of A occurring equals to the probability of event A occurring given hypothesis B has occurred times the probability of the hypothesis B occurring plus the probability of event A occurring given B hasn't occurred times the probability of event B not occurring. And I'll just go ahead and box those formula. Remember, these are the total probability formula. And so applying this formula for the event F with the hypothesis R leads to the probability that the students play football, so the probability of F, equals to the probability of F given R, so that's the probability that students played football given it rained, times the probability that it rained, plus the probability that students played football given that it didn't rain, times the probability that it didn't rain. And now looking at each of these different probabilities, we can see that we have the probability of the students playing football given that it rained. Indeed, that's 0.4, and I'll just write that below, that's 0.4. We also have the probability of it raining. Indeed, that was the first one given, that's 0.2, so I'll write that as well, that one's 0.2. We also have the probability that students play football given that it hasn't rained. Indeed, that's 0.9, so I'll just write that as well, that's 0.9. And although we're not explicitly given the probability of it not raining, we know that that must be the complement of the probability of it raining. In other words, we can add to our list of probabilities here and state that the probability of it not raining equals to 1 minus 0.2, that's equal to 0.8. So we have that probability as well, that's 0.8, which I'm writing in gray below it. Now we can actually calculate. Indeed, we can state that the probability that students play football is equal to 0.4 times 0.2 plus 0.9 times 0.8. That's equal to 0.08 plus 0.72. Finally, we can state that the probability that the students play football on February 15th is equal to 0.8. And that's the final answer. And that's the end of this worked example involving the total probability formula.